the crash course Quantum Mechanics by Shaeema Zaman Ahmed from the Science Melting Pot. Shaeema Zaman Ahmed is a physicist and a science communicator. She's originally from India and moved to Denmark to do her PhD in quantum physics education and outreach. She focused on, for example, games and simulations to educate students in quantum physics, and also taught about astrophysics and other areas. Based on her passion for science and outreach, she started her own company in science education, the Science Melting Pot. And from that company, she is also presenting here. In addition to that, she is involved in a range of initiatives, for example, to promote women in science and technology in Denmark.
Hi, everyone. It's really nice to be doing this session today, and I'm going to talk about visualizing quantum mechanics. It's something that I am really passionate about because I think quantum mechanics is considered to be so abstract and difficult, and the visualizing aspect makes learning quantum mechanics really different. Okay, so let's dive in. Before we dive in, a little bit of my journey. So I did my bachelor's and master's in physics from India, in a university called University of Delhi, and then I worked for 5 years at a science communication agency called Z Life Education. This was also in Delhi, and after working for 5 years, I wanted to do something more with research and also combining in science communication and education. So I moved to Denmark. To Aarhus University, where I did my PhD, and my PhD was on quantum games and simulations. And this was under a Marie Curie H2020 EU project, where I tried to explore how games can be powerful tools for all three areas in quantum physics: research, education, and outreach. And thereafter, I finished my PhD last year. And now I started my own company, and the company is about doing training courses in science communication, education, outreach, and diversity. So, and the company is fairly young now, 6 months, so it just started, but really excited for this. Yeah. So that was about me. And next is the outline. What are we going to do in this session? So we have an hour together, and then we'll be going through these 4 points. We'll dive into what is quantum mechanics, what are the properties of a quantum system. Some of this you may know from before, because we really have a mixed audience, but I thought it was a good idea to start from really basic foundation and build it up from there. And after we understand the properties of quantum system, we'll dive into a little bit of the terminology. And then we're going to look at one concrete example, the quantum harmonic oscillator. Great. So, what is quantum mechanics? Some of you may have heard the word before. Some of you may already know it. Maybe you're doing it in your undergrad or master's. So for some of you, it may not be so new. But if you think about it, and if you look at the scale, okay, so here on my left hand side, there's the scale where you have the meters, and then so if you think of a child, which is 1 meter, and then you just go down, lower the scale from a child, you go to a hand, to finger, to flea, hair, and go on, and then when you reach the atomic level, this is where we're talking about quantum mechanics. It's the atomic scale. But you can just imagine how one has to really, really, really look at, when we talk about quantum mechanics, we're looking at things at that scale, at 10 to the power minus 10 meters at the atomic scale. So this is where quantum mechanics, it describes the physics at this scale. And what we are generally more familiar with, or what we can sort of experience and relate to, is more the classical mechanics, for example, Newton's laws of motion, and so on. Okay, so we're really diving down into something really tiny, the atomic scale. And what are basic properties? These are some things we're going to now explore ahead in the presentation, but just a brief snapshot. Wave-particle duality, something dual. An electron or a photon can be both a wave and a particle. In quantum mechanics, we talk a lot about probabilistic. So about the position of an electron, for example, is the electron in this area, or in this electron cloud, we talk about probabilities. There's also uncertainty in quantum mechanics, and that's the inherent property of quantum mechanics. So there's uncertainty when you talk about position or momentum. And another important thing about quantum mechanics is we talk about things in discrete quantities called quanta. And this is where the word quantum comes from the concept of discrete quantities known as quanta. Great. Now, what makes a quantum system so special? So here I'm going to use an analogy of books on a shelf and then talk about these properties. And it's something that it is different from a regular classical system that we generally relate to. So let's start off. Okay, so now think of a shelf, and the shelf has different levels, and we place some books on a shelf, right? So this is exactly also what happens inside an atom. The atom will have particular energy levels, and the electrons will be in those energy levels. But there are these, and the electrons can only exist on those energy levels. Next, we have superposition. But now think about, you have a book here, you place it on the third shelf, but the book or quantum particle, can spread simultaneously through multiple levels. So even if you started out with having a book in the third shelf, or third layer of the shelf, let's say, but then after a while, you're actually going to start seeing that there is a probability that you can actually find the book on the first ladder of the shelf, or second, or even fourth, but with different probabilities. But when this happens, we call it superposition. It is these quantum states can exist in multiple states at the same time simultaneously. Now let's see, but now that we talked about superposition, and states can be in different, quantum states can be in can be in different levels. But what if we want to observe the system and see where is it exactly? So, but the moment we want to observe in the system, the particle instantly, we can only see that it exists in one of these four levels. So what we call it is that it can simultaneously be in multiple levels, but when we want to observe it, when we want to find out where it is, it settles in one of the levels. So what we call it as a state collapse, it collapses to one of the states. What's also special about quantum systems is that these energy levels, energy states, they react to parameters like electromagnetic fields or vibrations. And this is where quantum technology actually comes in. We exploit this physical property and build quantum technology, because then these electrons can be sensitive to magnetic field, and because sensitive to magnetic field, we can exploit this property to build technology. For example, to build quantum sensors. And this is a really famous experiment called the double slit experiment. And I think let's dive in. We watch its video. We watch the video, and then I'm going to ask you a few questions through the poll, and then we're going to really dive into this video and find out the different quantum properties. Yeah. Okay. So let's begin.
Hi everybody, and welcome to this video. Oh, I have a tennis match, but I also promised Matt that we could hang out. Oh, if only I could be in two places at once. Wait a minute, maybe you actually can. Do you see that wall over there? Huh. Awesome, right? A mark appears where the ball strikes. But now we place another wall up in front with a small slit which the balls can go through. The marks reproduce the same shape as the slit. Pretty logical. Just as logical as what happens when there are two slits. Okay then, let's try to do it again. But now in a swimming pool. Now it's no longer a ball, but a wave I want to send off. Check it out! The mark is stronger in the middle of the wall, exactly like with the tennis balls. But what if there are two slits? Then a whole new pattern appears. That's because the waves collide on the other side of the slit. Some places they reinforce each other, other places they cancel each other, and they create what we call an interference pattern. Get it? Okay, then let's zoom all the way into the atomic world and shoot electrons. First with one slit open. Super, and then with two. What? Did you see that? Even though I shoot one particle at a time, an interference pattern appears as if it were a wave. It's as if the electron divides itself into two and flies through both slits at the same time. We have to examine that. So now I use a camera to record what actually happens. What? Instead of being a wave, it suddenly acts as if it were a ball. It's as if the electron knows I'm watching and then it acts differently. Isn't that just bizarre? This means that an electron can be both a ball and a wave. And as a wave, it can be everywhere at the same time. But if you actually try to see where the electron really is, then it chooses just to be in one place in time and space. So the double slit experiment proves that you can actually be in several places at the same time. Unfortunately, that would require that I were an electron and no one could see me, so I think I'll just ask Matt if we can meet at the tennis match. Huh? Thanks a bunch for watching! It was awesome! Please subscribe! Bye-bye!
Yes, so I hope you enjoyed that video and this experiment. I hope if you didn't know about it before, it surprised you in different ways. So, okay, now just to make sure that you went through the video properly, we're going to do a quick poll. We're going to ask you a question, so just answer the correct answer. Yeah. Okay, and now coming back from the poll, now let's just reflect, debrief a little bit of what were the key points in the video. The first one, superposition. Do you remember when she talks about the electron that behaves like a wave, and it's almost like it can be in two places at once, and then it sort of goes through both slits, right? That's what superposition is. Okay, and then this can be, if in this particular video, and this can be extended to what we call as a quantum state can be a quantum object can be in multiple quantum states at once. Yeah, but we don't know which one, but we create a sort of mixture of states, what we call is a superposition of states, and what we call a linear superposition of states. And yeah, and the second part, wave particle duality. And I think this is when the first time I studied quantum mechanics, like long time ago. And I think this was something that it took me a really long time to wrap my head around. Like electrons can be both waves and can be both waves and particles. And that's also for any quantum object that we talk about, that there is this wave particle duality. The third thing is the role of observer. So when we observe, because now we know that an electron can be both a wave and a particle, and depending on certain experiments conditions, one property dominates than the other. But if you want to observe it, then it suddenly chooses to be one. For example, we saw in the video. But this essentially means that we are not observing whenever we want to try which state it is in. We're not observing these two states at the same time, but one of these states with a 50% chance. So there is a chance that it could be the quantum object can be found in another state. But what the observer does is it collapses it into one of these states with 50% probability chance of observing that the quantum particle. Okay, this is another video we're going to watch, which is on quantization. Remember I talked about discrete quantities, quanta, okay? And that's where the word quantum comes from. So let's again dive in. Yes, so this is about quantization. Now, we talked about how a quantum particle can be both a wave and a particle. So here we show there's a wave, and this quantum object can have different energies. For each energy, there is going to be a different kind of wave, and for each of them, there will also be a discrete, unique energy value for that particular for that particular wave. Okay. Uh, so this is also another very important concept in quantum physics. So far we've done superposition, wave particle duality, role of observer, and this was the quantization where there are discrete energy levels and energy values. Yes. Okay. So, right, like what we talked about, when a quantum object is put in a box, it behaves as a wave, and it can only have particular given shapes. So, it cannot have any arbitrary shape. It consists of these given shapes, and this each shape, for example, this shape and this shape, has particular a specific energy. The object energy is then quantized in discrete levels. Okay, and this was given by how do we know these energies? So there was in 1925, there was this physicist called Schrodinger, and Schrodinger designed this equation. And from this equation, we can find out the energy levels of a quantum system. Okay, and here there's a little little cartoon where this is Schrodinger, and we call it Schrodinger's quantum life, and suddenly jumping from one mood to another because you have, and one these moods basically is an analogy to the different energy levels that a quantum system will have. Great. So next. Now I also want to dive into a little bit about how when you think about an atom, a visual picture, quite often people think about a nuclear model and a planetary model, right? And so the theory and the model of an atom, atomic models have really changed over many years. So when we look at 1803, we had the solid sphere model. Then we had Thomson in 1904, Rutherford and Niels Bohr. So these are nuclear model and the planetary model. These are the ones that more graphically you would see. But when we talk about in quantum mechanics, we talk about a quantum model, which was developed by Schrodinger in 1926. And here, as you can see, we don't talk about electrons in orbiting the nucleus, but we talk about an electron cloud, and we talk about, okay, this is the more probable region. This region has a high probability of finding an electron. So we sort of move away from this electron revolving around the nucleus, but talking about an electron cloud. We talk about finding the probability. Yes. Now a little bit of math. So we had this basic. I wanted to just sort of give intuition about quantum mechanics and tell you a little bit about the properties and why is it so special. So we have superposition, we have wave-particle duality, we talk about probabilities, talk about uncertainty, and state collapse, which is when you're trying to observe a quantum particle, you cannot observe all the multiple states at once. You can only observe one of them with a particular probability percentage. Now we're diving into how, and now that we talked about these properties, we talked about a quantum system, but when we do quantum mechanics, there's a mathematical terminology that's used. It's a language that you use to talk about these things, to talk about a quantum system. Okay, so let's dive in. So let's consider that there is a box, and this is a quantum particle, and x is the spatial dimension of this box. For example, let's say this box is a meter long, so that would be this. Potential, for example, this is the box has hard walls that will give you, it's called, from where you will get the potential energy. So the shape of this box gives you the potential function, and then the quantum particle has energy. So what is the total energy of the quantum particle inside the box? And when we talked about a quantum particle can be both a wave and a particle, so we describe it by a wave function. So, and which just looks like this. And then you can have different wave functions for different energy levels and states. Okay, so these are the four primary things that the symbols and the terminology that we use. And now remember this wave function. So now we're going to do a square of this wave function, which is going to be probability density. So this probability density, this is also a very important part of, is one of the important things about quantum mechanics, is to, we always find out the probability density. And what does this tell us? It gives us the probability of finding a particle at a given time and place. So if you think about, so here we have four figures, which is from A, B, C, and D. And here we have a sphere. It's an atom, and then we look at wherever it's sort of dark in color, that the probability density is high. It means that there is the probability of finding a particle here, electron here is higher. Okay, and now this is more like a cross-section view, but here if you had to look at it as a map like this, where map of dots, then you'd see that this is very densely populated. Here you have another in densely populated, right? So probability density, so it's really probable to find the quantum particle here. Okay, so in this case an electron, we're talking about an atom, and these are density of electrons. But as you move out from the center, you'll see that the probability drops because the density of these points are decreasing. So this essentially means, if I want to do it in a graph, I would do the probability density at the center, where r is equal to, this is the center, is the highest, but as you move out the center and go outwards, the probability density drops. Right? And here you're talking about the full, do you add 4 pi r square, so you add the total area over the sphere, and then you get the total probability density. Yes, so exactly what we talked about is again like a recap of what I just said. And here we talked about can be found anywhere in the solid sphere centered on the nucleus. Then this electron density map plots where electrons could be. This higher density of dot indicates the physical location in which the electron cloud is most dense. And like I mentioned, this is C is a more graphical representation of B. Yeah. All right. So that was wave function and probability. So for a quantum system, we have the spatial dimension, and we have potential, and we have total energy. Then we need to know the wave function. From the wave function, we get to know the probability density. So there are all these things that we have to know. But the question is, how do we know this wave function of a quantum system? So if a quantum system is given to you, and but knowing this is really important, because this wave function describes the state of the quantum object. And here, okay, these small descriptions here are meant to describe the equation. Some of you might already know this, but maybe not. So then don't worry about these small descriptions. So this is called the Schrodinger equation. Schrodinger equation is how in Newtonian mechanics, or how we talk about neoclassical physics, it plays the role of Newton's second laws, which is force equal to mass into acceleration. And this is basically an analogous equation to that Newton's second law. All right. So if we just go through it term by term, okay, here we have something called h bar, which is Planck constant. This is a constant that mathematically used to give a relation between energy and frequency. Okay, this is m is the mass of the particle being described. This is a mathematical quantity called del square operator. Okay, so this acts on the wave function, and there's a mathematical and then we have the potential, which is basically the shape of the quantum system in some sense, if you think about it like that. And this describes the force that's acting on the particle. Okay, then this is I, which is an imaginary number. It's a mathematical quantity, and we talk about some of you may be already familiar with real numbers and imaginary numbers. So we have this imaginary, because when we're talking about wave functions, we're also talking about a certain phase of the wave function. So this phase is given by the imaginary number. And here del psi by del t is the rate at which how the shape of this wave function will change over time. So this is the equation. We quite often we know h bar, we know m, we know v, and then we can find out what is psi and how psi as a wave function, what is it and how it evolves over time. Yes, and here we have we talked about discrete energy levels and energy states. So this is one. Okay, so this is a potential, and we find that here you will have psi 0, 1, 2, 3, 4. Okay, so this is each energy level, and for each energy level, which is E0, E1, E2, for each energy level you'll see a wave function, the purple one, and then the right. So for each energy level there is a wave function. Okay, and this is known as the spectrum, energy spectrum. So this wave function is given by psi with subscript n. N refers to the which level are we talking about, and En, which means the energy of the corresponding level we're talking about. Okay, in this particular case we can actually see that they are equally spaced. Each energy level, E2 and E3, is equally spaced. E3 and E4 equally spaced, but this may not necessarily be true for all potentials, but we'll dive into that. Yeah, so think about energy being quantized in this way. You have these discrete energy levels, okay? And so an electron can exactly be on those energy levels and cannot be in any other energy levels, okay? So you can think about it as walking on a ramp as opposed to walking on a ladder, right? So on a ladder, you have these steps decided for you, and then you climb on those steps. So that in a similar way, an electron will also be in those energy states, like in a ladder, and then if you disturb it, sometimes it can also go to a higher energy state. But yeah, so think about it walking on a ladder instead of walking on a ramp, where energy is increasing, but energy is increasing in steps. Great. So, and now we'll dive into, yes, a concrete example. Quantum harmonic oscillator. So this is a very important model system in quantum mechanics, because this quantum model can gives a very good description of many quantum systems or many applications that we talk about. And here, for example, when you think about a diatomic molecule, for example, hydrogen, right? Hydrogen H2. So you have two atoms in here. That's a diatomic molecule. And there is some vibrations happen in the diatomic molecule. Okay, and these vibrations can be modeled by the quantum harmonic oscillator. Okay, so basically we're talking about the internuclear separation, which means the two diatomic atoms, and as we so along the x-axis, the internuclear separation is increasing, and then how the potential energy also changes. Okay, and in a harmonic oscillator, we can find out the energy values of these energy levels by this relationship. En is equal to n plus half h bar omega. N is basically, n is the energy level index for the energy level of this quantum system. Yeah, and here what you can also see is transition energy. Transition energy is basically sometimes an electron can go from the ground state to the first excited state. It could be because usually in an experiment, if you apply a laser with a certain frequency, then you can excite the atom to excite the electron to another level. Great. And here, okay, so here what we saw is this is the harmonic oscillator. Okay, so its potential energy changes with is proportional to the square of the spatial x. Okay, and a is just a constant that we have. Yeah. And here in this potential, we'll see that this is equally spaced, right? Okay. And in this is something what we call is a infinite well. So you can see that it's 0 for this interval, but otherwise it goes to infinite. It goes to infinity. So it's called an infinite well. And here, if you look, you'll see the spacing between energy levels is increasing. Okay, and here you have what we call a quartic potential, because it's x to the power 4. This is what is x to the power 4. And here you'll also see it's different, right? So so the main point of this slide is that depending on each potential has its own spectrum. Okay, so and this spectrum of energy levels and their corresponding wave functions, it has huge implications when we talk about when an electron gets excited to different states because of the spacing. And yeah, so you'll see these applications in the upcoming talks where we're talking about superconducting qubits or and so on. All right, so here also we have a little quiz. Now you have to tell us what is the spacing, what's the spacing in C and the spacing in D. So we're going to give you 2 questions, and just vote on the poll whether you find that the energy level is increasing here or decreasing, or increasing or decreasing here. Okay, and I'll just give a little bit of time because then everyone can send their results on the poll. And then now I go to the next one. Yes, so here, so for C, yes, the spacing between energy levels is increasing. But if and just maybe I want to shine some light on this, because even here it's increasing, but here it's increasing at a faster rate, right? You go from 19 to 30, but here you go from 21 to 30. So it is increasing, but it's increasing at a more slower rate as compared to an infinite. And here you would also see, here you, again, after a while, you see this is 5, numerical value 5, 10, and it decreases as we go up. Okay, so this is something, it's nice to get an intuition about how, when you think about a potential, how does the energy spectrum look like? Knowing that energy spectrum, you can draw out a lot of physics from it in terms of, okay, if the electron gets excited, what will be the oscillation of, let's say, sorry, when it's evolving in time, there is an oscillation period. What is the oscillation period that's going to be? To what levels can an electron be excited to, and so on and so forth. Okay, I think that was all for today. Yeah, we will meet again tomorrow, and this is a pre-recorded talk, so if you have any questions, just reach out to me on Discord, or also you can email me at info@sciencemeltingpot.com, and I'll get back to you with your answers. Yeah. Okay, so hi again. Today we're going to dive into part 2. Yes, of visualizing quantum mechanics. You guys were there in my part 1, and in this part 2, we're going to take it up a level higher. We're going to actually look at some quantum mechanical systems and look and explore all these properties that we talked about, like superposition, how does it evolve in time, and so on. Okay, so this is the outline. We'll also be doing some exercises, and actually, so there's a lot of work for all of you coming ahead at this session, and I hope you have fun. That's because, I've tried to pick some exercises that would actually make sense and also be fun for you, so it doesn't feel like you're in a classroom again. Okay, so let's start with the first exercise, one-dimensional particle in a box. So I'll just go out of this presentation and here. All right. So you can also go into this simulation through this link, and I think the link will be posted in the chat, so you can go to the link and explore these exercises. But what I'm going to do now is just give you a brief introduction of what we're looking at, what is the simulation, and what is the exercise going to be about. And then you spend some time in breakout rooms to do these exercises. And then hopefully you will learn something out of these exercises, and then we come back and discuss what you learned. All right. So what we're looking at here, it's called a one-dimensional particle in a box. So this one-dimensional particle means we're talking about one dimension, which is this one. It's yeah. So imagine a box, but we're just looking at it as one dimensional. And this is a box that has infinitely high walls. Okay. So yes. So what we call is an infinite well potential, and in this potential you have these energy levels E1, E2, E3, and it keeps on increasing to higher energy. You can see the energies here, the energy scaling here. Okay, and then whenever there's this quantum number n, it refers to what particular level we're talking about. So for E1, we know this is the wave function. For E2, this is the wave function, and so on. So gives you a sense, a sort of visual understanding of how do the wave functions change as we go up on quantum number n. Okay, and at the same time, we can also see the probability density. So if you remember from part one, we talked about probability density, which is basically the modulus square of the wave function. So but let's see how it looks like. So as it's the modulus square, you can see this part, and then the amplitude is given by under root 2 by L naught, and this is the uh, probability density. Okay, so, and you can also play around with it, like make the infinite well. Now this is narrow, but let's make it wider, and then let's make it even wider, so you can see how the wave function changes, probability density changes. And all right, so yeah, one can also look at the probability for a particular region. So you can expand this, right? And then so this blue shaded part is where you're looking at the probability density over that shaded region, and you get, you know, it's 0.41. So the total probability is always 1 over this whole spatial dimension, and then you can choose to look at whatever region you want to explore. Okay, so consider, I'm just reading it loud now. Consider a quantum particle of mass m. The quantum particle of mass m is confined to a one-dimensional region of zero potential energy between x equal to 0 and x equal to L. So which is given by 0 to L. Okay, let's hide this for a moment. The graph at the top shows you the wave function for the selected energy level. Okay, so I'm just reading it out from here. And the ground state corresponds to the quantum number n equal to 1. Yes, that's the ground state. And first excited state n equal to 2, and so on. And now we're going to explore how does the amplitude, which is this, sort of the height of the wave function, how does the amplitude and wavelength change with increasing quantum number? Okay, so this is the wavelength of the first wave function. So this wavelength is going to be from here to here. Okay, and for example, also from here is going to be here to here. This is the first wavelength, and then the second would be here. Sorry, first is from here to here. All right, so for anything, you can always click on these question marks when you're exploring, and then it'll give you more details about the experiment. Here you can also click on these question marks, and it's giving you the energy relationship. So something you can explore on your own. Okay, so just wanted to show you what's out there. And then now we dive into the challenges. Let's do the first one together. Okay, here the question is, consider a box of fixed width as shown here. Choose one or more. The larger the quantum number n. Okay, this is quantum number n. Basically, we're talking about the energy level. Okay, like n equal to 1, n equal to 2, and so on. So larger this quantum number, just look at how the wavelength is changing. Okay, or the amplitude is changing. So when I change this, what is changing here? So when I observe, let's check it out now, the options. the smaller the wavelength of psi x. Yes, that happens, right? We start from here. This wavelength is larger, and then it decreases as we go up. We can see wavelength decreases, but frequency increases, right? Of the wave function. Okay, so I would select this. Yes, this is happening. The larger we go, the higher the quantum number is. We just said it's smaller, so it can't be greater. The greater the amplitude of psi x, is the amplitude changing? This height, it remains the same no matter what. We go up the energy, up the quantum number, or stay below. So this is also not true. What happens is we're going up quantum number, and yes, and the energy is also increasing, right? So here you can see the energy scaling is 4 times E1, then it's 9 times 3 to the power square E1, and so on, right? So as we're going higher up, higher, larger quantum number, the greater the particle's total energy. Okay, now let's see. Ta-da! And yes, so this was correct. And similarly, you're going to explore these other exercises as well. Okay, here you're going to talk about when the width of the box changes, what changes. Okay, and then you're going to talk about what is the probability for a particular shaded region, and so on. And okay, great. So now we're going to do the second exercise, which is the superposition states in an infinite well. Okay, so let's dive right in. Again, I think you'll get this link on the chat. So you can have you'll get to know which simulation to play around with. Okay, so we did one exercise, and this is the second one, and I would highly recommend this. It's called It's made by a professor called Antje Cohen from University of St Andrews, and I think they have their simulations. I really like their simulations, and they have an entire library of them, so you can explore all of them after this session if you want. All right, so this is the second exercise, and what we're going to talk about is the infinite square well again, that which we did in the first part. But now we're going to talk about superposition states. Okay, so remember we said that a quantum particle can be in multiple quantum states at the same time. All right, so here we can select a quantum state psi equal to psi 1, and we can select the contribution we want from psi 1 and psi 2. And so if you want a superposition of the first and second states, or first or third states, or second or third states, okay? And then here you can sort of decide to, so let's say if I do wave function 1 and wave function 2, you want to, you can select here how much of the contribution of wave function 2 do you want in the superposition. Okay, so one thing it could be an equal superposition. It's equally the probability of finding the quantum particle in wave function 1, in psi 1 or psi 2, or you can also have an unequal probability, but then here you can select that, okay, by just using the slider. And as you can see, depending on what the contribution you choose, you select this. Okay, I'm just going to stop it now, like as in the time evolution, but see, I can select depending on what contribution you choose, the wave function is superposition wave function is going to look different. Similarly for psi 1, see, we have something like this that's happening. So it's really fun to play around with this depending on the contribution you want. Now I want the contribution to be this way, and then you have an oscillation that looks like this. All right, so yeah, similarly for psi 2 and psi 3, you can, so creating a superposition, you can sort of create your own superposition. Do you want it to be an equal superposition of two states? You want to be one state to be more dominant than the other, and so on. So mathematically, what we say is that we consider a quantum particle confined to move in one dimension in an infinite square well. Okay, here again we're talking about walls x equal to 0 to x equal to L, similar to the previous exercise we talked about. And this graph shows the probability density, which is psi modulus square of the particles. Here we can use the buttons and sliders to choose different quantum states, including energy eigenstates and superposition states. So when we select these numbers here, can you see under root 2 pi 10? This is basically how much of that state do we want, what we call coefficients of that particular superposition. So here Cn and Cm. So this is mathematically we would write it like this. And then here we're going to explore for which quantum states does the probability density change with time. And another question, how does the oscillation frequency relate to the energies in the superposition? Okay, so depending upon, this is one with psi 1 and psi 3, this is what the oscillation period looks like. And then we have something like this. And then we also have something, this is much slower, like you can see, right? The oscillation. It is oscillating. You have one peak of the wave function going up. And for this, actually it's much faster. And for here, it's faster, but it's slower than what we saw. Yeah. All right. So this is what we're going to explore. You can also show expression for, so this is all the math behind it. Okay. This thing that is evolving in time, it's basically based on this relationship here. All right. And this is the coefficients that we choose, C2 and C3, which means how much of psi 2 do we want, how much of psi 3 do we want. All right. So under root 2 pi, and then it calculates, and it's oscillating. So this oscillation period basically depends on the energy difference between these two states. So for example, in this particular example, we're looking at psi 2 and psi 3. Therefore, we're going to take into account the energies for energy level 3 and energy level 2. Okay. So similarly here, it changes energy 3 and energy 1. And you can see it goes at a much faster rate, right? That's because the energy difference is quite high between E3 and high. So that's why this term is going to rapidly change, and we have a higher frequency, a higher oscillation frequency. Okay, so sometimes it might feel too much to look at all these things together, right? So I would suggest sometimes if you just want to look at the wave function, maybe you can stop the wave function, also look at it. Yeah, this way, this is the expectation value. We did not do this in part 1, but I just want to talk about it. This is a concept where it's a mathematical calculation that one does in quantum mechanics, and we try to find out what is the expectation value of finding the particle. All right, so this is, in this particular simulation, is shown by a dashed line. Okay, so if we have a superposition of psi 1 and psi 3, the expectation value that we will get is here by L half. Okay, and remember we talked about uncertainty, right? Quantum mechanics, we talk about a position uncertainty, and this uncertainty is this shaded region. Okay, so great. This is what the simulation is. We now explore. Let's do one exercise. For which of the following states of the particle in an infinite square well does the probability density explicitly depend on time? Choose one or more. Okay. So just to go back on this, if we just select one state, oops. Okay, so this question also changed. Yeah, all right. So where was I? For which of the following states of the particle in an infinite square well does the probability density explicitly depend on time? So this is not a superposition state. Okay, so these are all superposition states because it takes psi 1, psi 3, psi 1, psi 2. Yeah. And superposition states are going to evolve on time. So let's find out. Yes, correct. The probability density is time independent for energy eigenstates. Okay, now let's try another thing actually. So selecting this, this is a non-superposition state, okay, which we call as an eigenstate, which means that wave function psi 3 is the wave function that corresponds to energy level 3. And if I do this, okay, so these energy eigenstates, which are not superposition states, they do not evolve over time. Only superposition states will evolve over time. So that's what the question was about here. For which of the following states of the particle in an infinite square well does the probability density explicitly depend on time? And this depends, a superposition explicitly depends on time. That's because we have this energy term here, En, right? So when you have an energy difference, then you will have this t term that would act on it. And then you have the evolution that happens, the time evolution that happens. Okay, so here is the other one. Okay. Remember, we saw this in the simulation. And here the question is, the graph shows the probability density of an unknown state for the particle in an infinite square well. Is this state an energy eigenstate or a superposition state with respect to energy? So this is moving. Now, do energy eigenstates move? Energy eigenstates, like we talked about, if it's a non-superposition state, okay? Does that move or it doesn't? Just think about that, okay? And this is moving, and we saw it during the simulation, and it is a superposition state with respect to energy. And let's see. Yes, the probability density is time independent for energy eigenstates and time dependent for superposition states with respect to energy. Okay, so have fun, explore these simulations. I really like them, so I hope you also have fun. Okay, and if you have any questions, just drop a message in Discord. I hope I can answer it right away, but if not, I'm going to answer it in a few days. That's because I'm traveling right now, and that's why I decided to record this presentation. But if not, just ask your mentors in the group and we'll take it from there. All right, okay, going back to this. So after we do this, so this is the last exercise we're going to do on superposition states, and then the next part is going to be on spin, which will be just after you finish doing these exercises. So we'll come back to do that. Yes. Great. Okay, so now we're back after the exercise, and now we're going to explore something new called spin. So you must have heard about we talk about spin of an electron. So it's an intrinsic property that defines the angular momentum of an electron. Okay, so mathematically, it will have a what we call is a half spin half particle. Okay, so and this here I'm going to introduce a Bloch sphere representation of the quantum states for a spin half particle. So now this Bloch sphere representation, it you think about it, is you have a state, okay, a quantum state psi. All right, this is some kind, it's a notation. We didn't do this, but so I'll just briefly touch upon it. You have this notation called the bracket notation. That's why you have this sort of vertical line here, and then you have this. Some of you might be familiar with this. I'm not diving into it. But this is the wave function psi state, okay, and it has a component of an upspin and a downspin. So when you're talking about spin, the Bloch sphere representation is how is the spin aligned. You can have if you have a sphere, so you have the north pole, south pole, is the spin up or is the spin down, okay? So it's represented on this sphere, and this is represented by these arrows that are given up and are given down. So that way I think it's quite artistic, like up and down, so it's just represented by arrows, right? And here we're also going to be talking a little bit about spherical polar coordinates, okay? So there are two angles that we're going to look at, and based on these angles you can have a wave function in that in the Bloch sphere, okay? So I think let's just dive into the step-by-step explanation. So you can see that the Bloch sphere representation gives a one-to-one correspondence between points on a sphere and the state. All right, so you have theta and phi. So if you look at the sphere, pay attention to these blue circles. There's one circle that's going this way, and then there's one circle that's going this way, okay? And these are the theta and phi angles basically determine the quantum state, because then you can have, depending on the theta and phi angle, you have a particular superposition of a spin up and a spin down state, okay? And the outcome probabilities of where the state is given by these numbers. These are the theoretical measurements of outcome probabilities. Okay, now let's go here. So when we talk about the north and the south poles, which I was just mentioned, and we have these angles theta equal to 0 and theta equal to pi, okay? So just if you remember, this was theta, It's this vertical circle we're talking about. Okay, and at theta equals 0 and pi, we have these spin up and spin down states with arrow up and arrow down respectively. Okay, and in both cases phi can take any value. So if you remember, phi was this, right? So we're talking about one circle like this and one circle. Oops, sorry, I got confused myself. Yeah. Okay, and then we put these values here. Okay, and that's when you, so we know that theta is equal to 0, so then there'll be a 0 that'll be sitting here, and that's how you get a spin up state or a spin down state. Basically, we saw this expression, we put the value of theta and phi, and then we put the value of theta and phi, and we get the up or down states. Okay, and here the angles are changing, polar angle. And now what we're doing is we're going to change this angle. We're changing phi, which is, so now we're talking about another angle. We put this value, and then we have a quantum state that is that will be sort of a superposition of the spin up and the spin down states. Okay, so you can see that north and south poles represent states up and down, spin up and spin down respectively. In both cases, phi can take any value. You can see that all the points here is the equator, theta equal to pi by 2 corresponds to equally weighted superposition. Okay, so when we have this particular angle, when theta is equal to pi by 2, we have an equal superposition. You can see the coefficients here, 0.707, 0.70. Also the probabilities, you can 0.50, so it's an equally weighted superposition. Okay, like we talked about, you can have a superposition, sometimes it's equally weighted, which means there's probability of a 50-50 chance of being in this or this, or depending on how it is weighted, you can find the probability of finding the particle in a particular state. Great. So here, if you were to measure the spin component along the x-axis, okay, again, if you see here in the Bloch sphere, the eigenstate, you have a plus and minus eigenstate, and this corresponds to the outcome, the spin component along the x-axis. Okay, and here it's basically just trying to show you all these plus and minus states. Great. And here, if you were to measure the spin component along any arbitrary axis, here there's any arbitrary axis happening. So we talked about the x-axis or spin component along the z-axis. Then the eigenstates correspond to the outcome Sn minus h bar by 2. Okay, so here, so this model is really used in describing superposition of spin, and we're going to look at it again a little ahead when we're talking about quantum computing. So it's not to overwhelm you with a lot of things, but just to make this picture stick in your minds about when you're talking about spin, how do you represent it, the graphical and mathematical representation. Great, so that was the Bloch sphere, and we're going to explore another one, which is okay. So now we're going to, so we looked at the Bloch sphere. So now we're going to actually look at how does time evolution of a two-level quantum state, which means a particle that's in a superposition of a spin up and spin down. Okay, how does that evolve with time, and how does it look like on a Bloch sphere? Okay, so here's a simulation. Here I can just show you. You can explore it as in really sort of in detail, and it's nice if you do it yourself, because then the more you explore it yourself, the more understanding you'll get, and the more sort of you can see what changes when you change what, and so on. Okay, but here just a brief introduction. You have the initial state size 0. You can select that the initial state has a spin up or spin down or superposition of a spin up and spin down, and so on. Okay, so this is the input state. So whatever input state you choose, you can see the visuals changing here, and you know where the input state is. Okay, and now we're going to consider this. So what we're doing is we're considering a spin half particle of some charge E and mass m whenever it has a charge, and now we keep this in a uniform magnetic field, so which is mentioned here as magnetic field strength. And whenever we have a superposition state, okay, and we have it and it's under magnetic field, it's going to it's like it's going to evolve in time. And that's because this, due to the spin, this particle acts like a small bar magnet when in an external magnetic field. Okay. And depending on that, this oscillation will depend upon the superposition of these two states, and then you have this evolving in time. Great. So this is the sort of overview, and now let's get into step-by-step explanation. This we looked at in the first part, right? We have a theta angle and a phi angle, and then depending on that, you have a particular superposition of either spin up and spin down. So and now what we're going to do is we're going to see how does it evolve in time. So we first take angle phi equal to 0 at time equal to t equal to 0. It looks like this. And now when you're talking about time, we have this phase factor. Okay, this is a mathematical thing where they're rewriting this in a particular way. And so when we have with time, this angle phi is going to move with this relationship omega t, which is the frequency. Okay, this and in the Bloch sphere representation, this implies that the spin state rotates around the z-axis. You can see that it splits. This is the z-axis, and it's going to rotate around the z-axis with angular frequency omega. Okay, so this is how you can calculate the time development of a two-level quantum states. Here we're talking about two levels, which is the spin up and spin down. These are the two levels we're talking about, and how does it evolve over time. So try to play around with this. Okay. Here you can also see how the probabilities change over time, and with the x component of spin. Then I don't know if you noticed in the first simulation where we showed you, okay, maybe let's go back to this. Here, even if it's magnetic field strength, it doesn't move. But now we create a superposition. It's going to start evolving in time. All right. And this is what precisely this statement here is trying to say. If the initial state is an energy eigenstate of either spin up or spin down, you can see that the quantum state does not change with time. Okay, this is really important. A superposition state will evolve in time, but an energy eigenstate will not evolve in time. And this is why you must have heard energy eigenstates are also called stationary states, which is yeah. So anyone, this is mostly relevant for people who are doing their undergrad or graduation, where these things will sort of make more sense. Yeah. So I'm not really diving into detail about it. It's just an introduction, so that you just have the visual picture in your, you remember it when you look at it again, maybe in a different session, or when you're doing your coursework. Okay. So that was about spin, and now we're going to actually move to something. Okay, I'll just close this. We just move to this, and now I'm going to talk a little bit about something called entanglement. Okay, entanglement is something that, again, we didn't do this in detail in part one, but I just want to touch upon it because it has certain applications. So let's dive in here. Okay, so here, let's say you have two entangled balls. Okay, so you have, so entanglement would mean, so let's consider of two balls which has slightly half red, half yellow. Now I'm trying to relate this with spin, so we're saying that the red part signifies spin up and the yellow part signifies spin down. Okay, and now for now they're both in a superposition of red and yellow states. Okay, both these boxes. So there's a box, there is a ball in each, and if there are, when we say they're entangled, let's say, where when we say entangled, it may basically means that as if these two balls are connected in some way. Okay, like when you change the state of one, you automatically affect the other one. Okay, and this has huge implications, which will come to it. Okay, so just wanted to give a brief introduction to the entanglement aspect. Okay, so let's say you have two entangled balls, each in its own box. In this metaphor, the balls can be either yellow or red once observed. Okay, so remember when we talked about state collapse. So now we don't know, this is in the balls are in superposition state of red and yellow, and we're going to try to look at this. And they're in a state of superposition. When we try to look at it, I try to look at it, okay, and I say mine is yellow. And then if these balls are entangled, a friend of mine is also looking at it and saying mine is yellow too. And this is what entanglement is. It is somehow as if these balls are connected. And what is even cool is the objects can remain connected even over vast distances. Okay, so first you need to create them, you need to entangle them. And this can be done in certain experiments, and once they're entangled you can play around with one which affects the other one. And I think that is really cool, and it has implications in especially quantum computing. Yes, and now we talked about, so now when we think about, okay, sorry, I maybe when that I wanted to also emphasize one thing here. So entanglement here, so we talked about how these colors yellow and red, right? Now think about when we talked about spin, the spin, when it's yellow it means spin down, or when it's red it's spin up. Okay, so you can have a quantum system where you have the spin entangled, you have two electrons and their spins are entangled. And here, okay, this is again, you must have heard of a qubit, right? I mean, when we talk about quantum computing, we talk about a two-state quantum system, and it's exactly what we saw in the Bloch sphere representation. Here we're talking about superposition. It's overlay of different states, which means an overlay of spin up or spin down. Okay, and then when we measure it, we get a clear definition of the state. Okay, now 0 and 1. Now, just to put some perspective on this, when we talk about classical computing, we have binary, yes, we have binary states, either 0 or 1. But when we talk about quantum computing, we have a superposition of states, which means that we can have 0 and 1 at the same time. And this basically, how it helps is, so here when I talked about binary system, and you can get either 0 or 1, but here in a qubit you can have a superposition of 0 and 1. And how this helps is that it gives a parallel arithmetic operation, so you can do many arithmetic operations at the same time. So you can do many operations at the cost of one, because you have 0 and 1 in a superposition. You have an overlay of different states. And this has, so once we have quantum computing, it can handle large amounts of data. That's because we can process data much more accurate, much more, it can simulate much more accurately, but it can also handle large amounts of data efficiently. And remember I talked about entanglement. This entanglement is, just wanted to also mention here, the effect of measurements on the entanglement state. So for example, you have two qubits that are entangled. So taking a measurement of one qubit causes it to collapse into one of the two states. Okay, so if you change the measurement of one, it instantly reflects it. So over time, so what happens is the quantum entanglement allows to only measure one qubit. So how this becomes really powerful, because we can, because it's entangled, we can only measure one qubit, and then by measuring one qubit we can figure out the value of the other qubit in the entangled pair instantaneously. So it become more efficient to do measurements when we talk about qubits. Okay, so that was it for today. We covered all of this. You did some exercises yourself, and I hope it was helpful. um, I might have gone too fast over a few things, I have a feeling. And if that is the case, if you have any questions, please write to me. Again, reach out to me on Discord, or write to me at info@sciencemeltingpot.com. You also have some mentors right here who are moderating the session, and they will also be able to help you. But I'm always there, so just reach out to me whenever. Okay, but thank you so much, and bye.
Thank you, Shaeema, for that great introduction to quantum mechanics. All basic concepts being covered, from superposition to particle wave duality to Schrodinger's equation and to different potentials. I will share her presentation slides, and then we will answer Q&A questions that showed up in the Discord so far. So one question was about the probabilities. Here, a hydrogen atom is shown, one example in quantum mechanics that very well describes the reality. Wave functions in quantum mechanics are described by psi, But in reality, we only measure densities, probability densities given by psi squared. Here it shows that close to the nucleus, basically at distance r equals 0, we would have a very high probability density to find electrons. And then it goes down with distance. What you see depicted here is the radial probability density, where we look not only what is this probability, but the probability over an entire radial shell. So close to the nucleus, we only have very little space, right? So, the probability times that very little space is still pretty low. While if you get farther away, where you have a higher where you have more space with a reasonable probability, that is eventually the integrated highest probability to find electrons. So this gives you this 1s orbital that you see depicted here. And later on, you would see a second peak coming up. You already see it indicated here a bit, which would be the second orbital. So this shows it is an electron cloud, but with different probability densities in different radial spots, which give you kind of shells, but that is simplified. It gives you these orbitals of electrons. Then there is a question about these potentials. You have seen different shapes of potentials here. And maybe a first question is, what does this actually mean for electrons? What is this about? And is it real? I can share one other tab for you to show you that is real. Give me 1 second. I stop sharing here and go to my entire screen. You should still hear me, I think. Yes. Okay. So these potentials are tell where electrons, what the potential landscape is for electrons to be in. It could, for example, be a molecule. Think of a very simple molecule, for example, carbon dioxide or just 2 hydrogen atoms. The only place where electrons can be is in that molecule and not outside. And they are delocalized over that molecule, but they are not there anymore a centimeter away. So the molecule is basically a potential like this. Here in the middle, you see that you see the potential landscape 0 in the middle for x smaller than a, or 1 here. This is basically the molecule would extend here from -1 to 1, and infinity otherwise. That would be outside of the molecule, where there is nothing. So the electrons of the molecule can be either in the molecule between -1 and 1, and not outside. So that is defined by this potential. And now we can, and this is very simplified, a more sophisticated version would already be this quantum harmonic oscillator, where you see the potential is a bit more, a bit smoother, and different potentials describe different different implementations. Now, how can we, for example, create that and also see that that we have waves there, even for electrons? For photons, you are well familiar with that light is a wave in principle, right? And you learned today that you can also describe it as a particle. The other way around, electrons, you are usually used to that they are particles, but we can also describe them as waves. I would like to show you that we can even see those. So this is an image of electronic waves. This is a piece of copper, where electrons are as a kind of surface gas at this surface of the copper. So basically a thin layer of electrons at this surface of copper. And now we put atoms on top. This is done in in a special device, a scanning tunneling microscope, where you can see atoms and also move them one by one. When you think about electrons being particles just sitting around, maybe you wouldn't think much would happen, but electrons are waves as well. And here you can see their wave nature visualized. The waves of electrons are reflected by this wall of atoms, and they start to interfere, something you usually know from light, which is a wave. So they start to interfere. You have a standing wave of electrons, and their probability is measured. And you see we have higher probability in some spots and lower probability in other spots. I will have a look at the Discord to see more questions. Indeed, the graphs are the potentials, photons. It is great that you are also helping each other. And I see there are some questions about the quizzes. Let me tell you about that. Today, there will be one quiz on Canvas about the second lecture. So what you learned about the crash course, quantum mechanics. This quiz is mandatory and will count towards your certificate, quantum computing hardware. I will now show you where you can find it. You go to the Canvas, which you should see now here on my screen. You go to assignments, and they might be shown by date at the moment. But as you see, the due date, the eventual due dates are all 25th or August 7th. So this doesn't sort it on the day yet where we are now. So what you do instead is you show it by type. What we had today was in the module Quantum Computing Hardware, the first quiz, Crash Course Quantum Mechanics. Ideally, you do it right away today. It will only take you 3 minutes, I think. If you don't have time today, you still have time until August 7th to do it. So you click on the quiz, and there will be some questions which you might be quite familiar with already. So I invite you to do this quiz right away today. Additionally, especially for those of you who are in a different field, like computer science, or who are in physics but haven't learned much about quantum mechanics yet, we would like to invite you to do some additional exercises. And this is optional. So this is for you to learn more about quantum mechanics. We will share the list with you on Discord and in the YouTube list. I will give one of them as an example. You should see my screen now about the one-dimensional particle in a box. These are interactive exercises about the things that you just learned. So for example, you just learned about this potential that is very steep, this staircase potential, which would be the simplest model of a molecule where you can have electrons in this space, but nothing outside. So here the potential is 0, and there the potential is infinite. Now you can see how electrons behave at the different energy levels. The lowest here gives you half a wavelength, then the second, a full wavelength, third, etc. And you can also see the probability density, the wave function squared, how it behaves, where are the peaks, and where are the nodes. You can make the well wider, and you will see that the energies decrease. More space, lower energies. You can make them smaller again, and they increase again. There are several more of these exercises to show these basic principles of these potentials. And this will be very useful to familiarize yourself with for the lecture in superconducting quantum computers, where different ways are used to create the perfect potential for qubits in superconducting quantum computers. So for today, we ask you to do the quiz on Canvas, and please browse the exercises, join the Discord to discuss the exercises there in the text channel, but also in voice channels to discuss with your peers. If you like the lectures today, share it on LinkedIn, Instagram, other social media that you are on. Tonight, we will show the YouTube video of Worley's talk and also the crash course in quantum mechanics. So you can share it with your friends and everyone you want to know about that quantum computing is an amazing topic that you should enter now. For tomorrow, we have 2 other very exciting components coming up. Tomorrow's session will start with WOMANIUM quantum research spotlights. Our team consists of quantum researchers, students from bachelor to postdoc level in a variety of areas, from quantum optics to quantum materials to doing research at IBM, INQ, Danish Technical University in Italy. And everyone has very exciting research updates to share, from cognitive neuroscience with quantum computing to how do electrons behave at 10 millikelvin in a special quantum potential that you just learned about. That will be half an hour, and you will also have the opportunities to ask questions about all these different topics. And after that, we will start the quantum programming training with QWorld, QBronze, Jivan Rashid, who will take you from classical and quantum systems tomorrow, and then all the next days to Shor's algorithm. Thank you very much for attending this great session today. We look forward to all your questions on Discord and also your discussions in the text and the voice channels. Please do your quiz and share everything you enjoyed today on your social media and in the Discord. Thank you very much. We will close the session and we'll see you tomorrow at the same time for the WOMANIUM research update and for the QBronze first lecture. Enjoy the rest of your day and your evening. Alex, thank you for organizing everything. Thank you very much.